Hi again, guys. So in this video, well, in the last video we saw just the statement of the axiom of pairing, and in this video we're going to introduce the set that you get from the axiom of pairing. It's called the unordered pair of A and B. Okay. So first we'll make the definition, but then after we'll need to kind of justify the definition. Okay, so let's start with the definition. Okay, so A and B are sets. Okay, actually they could be the same set or maybe different sets or whatever sets you want. Okay. The unordered pair of A and B, it's denoted, well, it's just a set with two elements. The first element is, or one of the elements is A and the other element, another element is B. Is the set such that X is in AB if and only if X equals A or X equals B. Okay. Okay. So I guess I should have mentioned there's like a subtle point here before I move on to this proposition. But first you can ask yourself this question. Why do we need an axiom to define this? Okay. If you think about it, so I don't know, this is just my rough answer. But you can put P of X to be X equals A or X equals B. But in order to apply the axiom scheme of comprehension, we need a set where A and B both live inside. Okay. We know that assuming that all sets live in some universe of sets leads to a contradiction. So this axiom, we need this axiom to guarantee us that if A and B are sets, we can find a set which contains them both. Okay, the set that we get doesn't contain everything, just these two things. Okay, so we can find a property, but we also need a set to contain them both, has elements. Okay, and this axiom provides that for us. Okay. And let us prove this little proposition. Okay. So we've defined the unordered pair of A and B, but the axiom only guarantees that an unordered pair exists. As usual with these things, we need the axiom of extension to guarantee that the unordered pair is unique, and that would justify our notation for the unordered pair. Okay. So basically, let C and C prime be sets such that A X is in C if and only if X equals A or X equals B, and part B says X is in C prime if and only if X equals A or X equals B, and then C equals C prime. Okay, and I mean, this is pretty much the same as the proof we saw for the axiom schema of comprehension. We see that X is in C if and only if this is true. Call this P of X, say. So X is in C if and only if P of X, and P of X is if and only if X is in C prime. So X is in C if and only if X is in C prime, and the axiom of extension guarantees that C equals C prime. So proof by hypothesis, X is in C if and only if X equals A or X equals B, and that's true if and only if X is in C prime. And then by axiom of extension, C equals C prime. Okay, the end. Okay, so now we really get the unordered pair. Okay, and this is we know that so the axiom of existence gives us a set. The axiom schema of comprehension lets us take a set and kind of cut it down by looking at all the elements which satisfy some property. And the axiom of extension allows us to compare sets. This is the first axiom, well, we'll have others, but this is the first axiom which lets us build up, right? So let's just do, to end off the video, let's just do an example. Well, we know we have the empty set. We also know we have the empty set. Okay, then the unordered pair of these two things. Well, this is a what we get is a set such that X is in the set if and only if X equals the empty set or X equals the empty set. So we get a set whose only element is the empty set. Okay, we write that like this. This is a set with one element. The element is the empty set. Okay. Okay. So in general, the unordered pair of A and A is called a singleton, and it's written like that. Okay. Well, now we've constructed, so just from the axioms, we so far have constructed two sets. So let's construct another set. I mean, with this as one and this as the other, you know, why not? So another example. Take A to be the empty set and B to be the set whose only element is the empty set, and then you get a set with two elements. One of the elements is the empty set, the other element is the set containing whose only element is the empty set. Okay. Right. Okay. Let's stop this video here. The next video will keep on going with more axioms.